Hello and welcome back to the lab. On the bench today we have my Hewlett-Packard Model 334A Distortion Analyzer. The HP 334A was really the predecessor to the HP 339A distortion measurement set that I featured in a few of my previous videos. HP 334A was manufactured by Hewlett-Packard from 1966 up until 1988 for a period of 22 or 23 years. In 1966, this instrument sold for a price of $790. By 1988, that price had risen to $3,300, which is about $8,900 in today's money. So it's a pretty valuable instrument. Of course, it's obsolete because they haven't made it in 30, 40 years, but it's still a valuable instrument. The story about this one is um, I wanted to purchase one because I used to add to my collection because I used to work on these when I was at HP, and I used to service them and calibrate them and repair them. So I wanted to buy one, and I saw that one came up for sale from an equipment leasing company, and the price was good, but I called them up because it wasn't clear to me if it was functioning or non-functional. And he assured me that it was a functioning instrument. And so I accepted the offer and made a deal. And then he called me up the following day and said to me, "Well, um, we had our technicians check it out, and it's not working." And he said, "But we had another one for sale." So we went and brought that one out, and we had our technician check that one out, and it's not working either. So he said, "So here's what we'd like to suggest. We'd like to offer you both non-functioning 334As for the original price of the one 334A that was fully functional." And I certainly I took that deal because I wanted to actually start working on one of these. So I took that deal, and now I have two 334As. Um, of course, the repair to both of them was really relatively simple and straightforward, and I fixed them both. So now I have two fully functional 334A distortion analyzers in my lab. I say fully functional. This one actually has some minor problems with some random intermittent flakiness with the switch contacts and so forth. I'm going to have to open it up and clean the switch contacts. And that's why I have it on the bench today. And that's why I'm doing this review um, in this video. So before I open it up and work on that, I wanted to hook it up and make a measurement. And while I'm going through the measurement process, I can illustrate some of the features on this instrument and how it's used. So let's do that now. All right, so I've connected a coax connector from my 3325A synthesizer to through a 50 ohm termination into the input of the distortion analyzer. I'm going to switch it to voltmeter mode. We're first going to talk about the voltmeter function. So we're in voltmeter function on this instrument now, um, and it basically operates as a standard analog AC voltmeter with voltage ranges from 300 microvolts all the way up to 300 volts in 10 dB steps, and it's a basic analog voltmeter. It has a frequency range of 10 hertz to 110 kilohertz, so it's basically an audio AC voltmeter. So let's set my 3325 to 1 kilohertz, and the amplitude to let's go up to 3 volts, 3 volts RMS, and we have set the meter range to 3 volts, and you can see that it does read, in fact, 3 volts. I'll set it to 1 volt, 1 volt, 300 millivolts. Very good. 100 millivolts, etc., etc., etc. Let's go down to 1 millivolt. You can see that it works on every range. It's your basic analog voltmeter. Pretty self-explanatory there. The voltmeter has a basic accuracy of plus or minus 2%. And as I said, 300 microvolts full scale to 300 volts full scale in 10 dB steps. So that's the voltmeter function of this instrument. I certainly have lots and lots of voltmeters, so I don't really use the voltmeter function on this instrument. Okay, next function we have is the set level function, and that is used for a relative reference level setting, so that you can, when you're making distortion, you want to measure either in decibels relative to the fundamental or percent relative to the fundamental, right? And that relative reference level measurement is set using the set level function. So when we set this switch to the set level function, we set this switch must be set to the 12 o'clock position for either 100% if we're going to measure distortion in dB, or 0 dB. They're both at the 12 o'clock position straight up on this meter range knob. Okay, so let's put in a signal of 1 kilohertz and an amplitude of a good, healthy, strong signal, 3 volts RMS, something like that. And with the relative reference level, it's like an AC voltmeter, except it's not an absolute measurement. It's just a relative measurement. So you use this sensitivity control, the outer rotary switch control, and the inner vernier pot for fine control to set your reference level of your relative voltage measurement to either 0 if you want to measure your distortion in decibels, or to 1 representing 100% if you want to measure your distortion in percent. So let's use the 0 for decibels today. So we dial up the outer sensitivity step control until we're on the scale, and then we adjust the vernier for 0 dB. So that's our relative reference level adjustment for our distortion measurement. When we switch to distortion, it kicks in distortion function over here with the function switch. It kicks in a tunable notch filter, and we use the tunable notch filter to eliminate the fundamental signal of the fundamental frequency of the input signal. So in this case, we're putting in a 1 kilohertz signal, and we want to notch out that 1 kilohertz signal. Once you've notched out the 1 kilohertz signal, the only thing that's left to measure is the harmonics of that signal, which is the distortion. And because we've already set our reference level to 0 dB, we'll be able to measure our distortion relative to that 0 dB measurement. So we'll be able to measure our distortion with this instrument. So let's switch to distortion function. We have our frequency range switch over here. You can go from a frequency of 5 hertz all the way up to a frequency of 600 kilohertz to tune the notch filter frequency. So we use the main frequency knob and the little vernier fine frequency knob control to minimize our input signal. And what we're trying to do is tune the notch filter frequency to the fundamental frequency of our input signal, which is 1 kilohertz. So we can see that it actually reads 10 on the dial. 10 times 100 hertz is 1 kilohertz. We also want to adjust the balance control here, coarse and fine pots, to minimize our input measure, minimize our signal, to maximize the amount of nulling of the fundamental frequency at 1 kilohertz. So we've reduced the scale way down, the reading almost down to 0 on the scale. So what we want to do then is drop down our meter range control in 10 dB steps until we have an on-scale reading on our meter. Once we've done that, we're down about 40 decibels already into the noise. So we want to switch from manual mode to automatic mode at this point. And what that does is it allows you the instrument to automatically fine tune the frequency and the balance controls to maximize the amount of nulling of the fundamental frequency, to actually measure the actual amount of only the harmonics, only the distortion. So let's do that now. We switch to manual mode, from manual to automatic mode, and the needle continues to go down because our distortion is far less than what we were looking at already. All right, and then you continue to reduce your meter range in 10 dB steps until you get an on-scale reading. And there is our on-scale reading. And it looks like our distortion level, which is from our input signal, is something like negative 64.8 dB. So that's our distortion level, negative 64.8 dB. If we wanted to make the same measurement in percent, let's go back and reset our level to 100%. We'll switch to distortion, drop it down, switch to automatic mode, dropping it down. You can see right here the flakiness of the switch contacts in here that I need to work on. But in percent, for percent, we use this outer scale here, which is 0.1% of full scale, and it's reading about 0.061%. So that's the distortion of my 3325 at 1 kilohertz, 0.061%. So that's how we make a distortion measurement with this instrument. The other features on this instrument are an output jack, and what the output jack does is it provides you with the same signal that the meter is actually measuring at this point. So the meter is actually measuring the harmonic distortion amplified by 60 dB because we've dialed down the meter range all the way down to 60 dB. So you can use this output to connect to an RMS digital AC voltmeter, for example, or a wave analyzer or a spectrum analyzer to do further analysis on the harmonic distortion of your signal to see what the harmonics actually look like. So that will give you the harmonics amplified by whatever your main meter range switch is set to. The other features on this instrument, there's a high pass filter. And what that's used for is really very useful for if your input signal has some line frequency hum of 60 hertz or 50 hertz or 120 hertz or whatever. You can kick in this high pass filter. It'll pass all frequencies above 1 kilohertz, and it will eliminate any residual hum that's on your signal. So the hum will not affect your distortion measurement reading. It's a very useful feature for that, especially in old tube type equipment that may have a lot of AC hum in it. You can measure the hum separately and then filter that out and just look at the distortion, the harmonics. The other feature that the 334A has is an RF detector feature. There's a germanium diode detector inside this instrument, and that's used in the RF detector function. There's a rear panel input that's a triaxial connector. You can add an RF AM modulated signal and use the RF detector to demodulate that signal and measure the distortion of your AM modulated signal. I've never used that, and I can't imagine why anyone would really ever need to use that, but it's a feature that is available on the 334A. So that's the 334A and how you make a measurement. So let's take a look at the block diagram of the instrument and how it does what it's doing. All right, so here's the block diagram in the manual for the 334A. It actually is for the 333A as well. Um, the input comes through here, and in voltmeter mode, it passes through the input attenuator for ranges 1 volt range and higher, through the impedance converter, which is a FET-based input amplifier, to provide you with a high input impedance on the input. Okay, after the impedance converter, passed through a post attenuator, which is the range switch on the main range switch on the instrument, and into the meter circuit, and the meter also gives you the output voltage over here. When we switch to set level, instead of using the input attenuator, it uses that sensitivity step attenuator, which is over here, and to adjust your relative input level. And basically, everything else is the same. The input and the impedance converter, uh, the output of the impedance converter goes directly to the post attenuator and the meter circuit the same way. Now, in distortion mode, the input signal stays the same, but it passes through this other circuitry, the sensitivity vernier, uh, into a preamplifier and into this circuit over here. This is a Wien bridge circuit, which is the same circuit that we had looked at prior in the 200 CD oscillator. It used a Wien bridge circuit to form its oscillation. In that circuit, this element here was actually an incandescent light bulb, where in here it's just a resistor. The Wien bridge circuit is a 4 legs of a bridge. Of course, these 2 legs are resistive, a resistor here and another resistor here to balance out the bridge. These 2 legs, one of them is a series RC circuit, which is effectively a high pass filter, and this is a parallel RC circuit, which is effectively a low pass filter, where the impedances of those 2 legs of the bridge match the frequency. At that one frequency, you get an output voltage here that should balance exactly the output voltage here. So your input to the bridge comes in from the preamplifier through here. The output comes off these 2 nodes here. When these 2 nodes are balanced, there will be 0 differential between the 2. The bridge amplifier will have no output. That means we have actually notched out our input frequency. So if we put in an input frequency of 1 kilohertz and we tune these capacitors to that 1 kilohertz frequency, there will be no difference at our output. There will be 0 output. So we have notched out our input frequency. So that notch output of the bridge amplifier comes back through the post attenuator to the meter circuit. Now, of course, at these frequencies are only tuned to that one particular frequency we're looking at. So the harmonics, which are still coming into the circuit, will not be filtered out by that notch filter, and they will appear as a difference between these 2 nodes, and that difference will be amplified and shown up on the meter as the distortion. So that's how the notch filter works. In addition, the 334A has that manual versus automatic mode switch. In automatic mode, the instrument takes a sample of the output and adds it to a phase detector and another phase detector over here. And that phase detector compares the input signal to the output signal, and the difference in phase between those 2, it uses that difference to drive a lamp driver, which illuminates an incandescent light bulb, actually a couple of incandescent light bulbs, one to adjust the frequency and one to adjust the bridge balance of the input circuit, to automatically tune the input frequency using these light bulbs, which shine onto photoresistors. The cadmium sulfide based photoresistors inside the instrument. I believe it's the A6 assembly, the A6 module inside the instrument. And we'll take it, we'll open it up and take a look at one of those and see how they function. But simply to know that the automatic nulling function of the instrument is done through sampling with the phase detector, through to drive incandescent light bulbs, which illuminate these photoresistors to fine-tune the frequency and the balance of our Wien-Bridge notch filter. So that's how the 334A does its magic. Now, a couple more things I wanted to mention. The input is capable of making floating measurements. If you remove the ground strap between the low input terminal and ground, the chassis or earth ground over here, you can do floating measurements on your input. Also, the low common terminal input is connected to the low common terminal output and to the common the circuit ground inside the instrument, so that if you don't want to have a grounded output terminal, you have to remove this input ground strap from the input terminal's low common. I also wanted to show you the RF input connector on the rear panel. So let's turn the instrument around and put the, you can see it. All right, there we go. We got the universal tilt stand here. So here's the RF input on the rear panel of the instrument. It's a triaxial connector, which is not a standard BNC connector. So please don't try to connect a standard BNC connector to this RF input, because you will damage it. There are actually three bayonet lobes on this input connection instead of two bayonet lobes that are on a standard BNC connector. All right, so you have to use an adapter like this one, which has, I don't know how well you can see that, but it has two outer shields, an outer shield which is connected to earth ground and an inner shield which is not connected to earth ground, and it's only connected to the low input terminal of the instrument, and the output of course just has the one outer shield of the BNC. So that's how this adapter works. There's another type of adapter. This type of adapter shorts the outer shield to the inner shield when you use it. There's another type of adapter that has a little Teflon insulator that you visible in this central part of the unit, and that isolates the outer outer shield of the BNC is actually connected to the inner shield of the triaxial side of the connector, and the outer shield of the triaxial connector is connected to the earth ground and to the chassis of your unit. So depending on whether you want to make floating measurements or grounded measurements, you have to use the correct type of triaxial to BNC connector. Don't try to stick a BNC directly onto your RF input if you're going to use that. Also on the rear panel, we have standard input power jack, power socket, a line fuse, which I've already checked to make sure it's the correct fuse in this instrument. We have a line selection, voltage selection switch, 100, 120, 220, or 240. It is set to 120 volts, which is our standard here in the United States. Serial number tag 1140, that indicates that the production run for this unit began in 1971. This unit, I can tell you, is not manufactured in 1971. It's manufactured in 1982. I can tell that from the date codes on some of the components internal to the instrument. Now, before I open it up, I did want to take a second to hook up the input and the output of my 334 to my spectrum analyzer and sweep through the notch filter and show you on the spectrum analyzer what the notch filter actually looks like in the frequency domain. So we actually be able to see the notch filter filtering out the tracking generator, which will be set up on the input, and the spectrum analyzer will be set up to the output of the distortion analyzer. So let's do that now. Okay, so I've set up the 3585A spectrum analyzer to sweep through the notch filter of the 334A distortion analyzer. We have the output, the tracking generator output of my spectrum goes into the 50 ohm termination into the input of the 334A, and the output of the 334A goes into my 1 megohm input impedance input of the spectrum analyzer. We have a center frequency of 1 kilohertz and a frequency span of also 1 kilohertz. So we're going from 500 hertz to 1500 hertz, and it's sweeping through. The 334A distortion analyzer is in reference level, set level mode now. So we've set our reference level to the top of the screen. We have 5 dB per division vertical resolution. When I switch to distortion function with manual mode, the notch filter should kick in, and we should be able to see the notch as it sweeps through the 1 kilohertz notch frequency. It should notch out the spectrum analyzer input. And there is the notch. It goes down pretty deep. It goes down to negative 51 dBm when the reference level was set to negative 9 dBm. So it notches out by about 41 decibels, something like that, over 40 dB. Of course, we can't switch the distortion analyzer to automatic nulling mode because it'll attempt to track the sweep of the tracking oscillator, and that won't really work properly. But we also can't reduce the meter level. But in fact, the depth of the notch is specified by Hewlett-Packard to be greater than 80 dB below the fundamental. In this case, it looks like it's goes down at least 50 dB in manual mode, not even going into automatic mode yet, and I haven't really adjusted it very finely. But it will, in fact, go down way below 80 dB below the fundamental carrier frequency. So that's the notch filter as swept through on the spectrum analyzer. All right, so let's open this instrument up, and I will get to cleaning those contacts and get rid of all those flaky intermittent problems with this instrument. And I'll show you some of the circuitry inside while doing so. All right, so I've removed the top and bottom covers from the instrument, and I had to remove this one little piece of the side panel on the right side in order to remove the inner shield, because there's a screw that comes through the side. I removed all the screws from the bottom inner shield, and that should just come right out, and we can take a look inside. All right, so here we see all the rotary switches. They all have dirty contacts that will need to be cleaned. Um, this is the meter range switch. This is the relative sensitivity switch, and this is the function switch on the front of the instrument. These are the underside controls that I need to work on to get them all clean. One thing I noticed here, these are small value compensation trimmer capacitors to adjust for the frequency ranges on the sensitivity uh, rotary switch. Um, Someone has tweaked these incorrectly, I'm sure. They are bulging up so high, the little slugs are sticking up so high. I guess you could call them slugs, they're really just adjustment screws. They're sticking up so high that they actually contact the metal of the bottom shield, and that certainly is not correct. So I'm going to have to readjust those and get those down at least below the surface. Um, they were probably incorrectly adjusted many, many years ago, and no one has just really ever looked at that. But I'm going to go through the complete realignment procedure of this unit before, or like while reassembling it, and I will do a complete performance test to make sure it meets all its original specs. Okay, so that's the bottom of the instrument. We have power coming in on the rear panel. Oh, by the way, make sure you unplug your unit before working on it so you don't get zapped. You don't want this to be the last instrument you ever work on. Okay, that's just common sense, right? Okay, so, oh, well, let's turn it over. Here's the top side of the instrument. Inside this shield is that RF detector diode, that germanium diode that I mentioned at the beginning of the video for the RF input AM demodulator uh, input on the rear panel. There's also outside of the shield, there is a spare germanium diode that HP has provided in case you accidentally blow up your input by applying too much RF or something. There's a spare replacement diode. Um, that would make a great diode for um, a little crystal radio set. That's how I got started in electronics way back when I was 6 or 7 years old. I built my first crystal radio set together with my dad. You know, a coil, a capacitor, one of those diodes, and a high impedance earphone. Solder them together, and music comes out. It was pretty magical back in 1967. I'm sure that kids of today wouldn't be all that impressed with it, but I certainly was way back when. And that's what got me started in electronics, by the way. Okay, so that's a little bit of the circuitry inside the instrument. We have the main tuning capacitor for the wean bridge of the notch filter. It's 4 ganged sections. 2 are in the parallel leg, and 2 are in the series leg. They are tied together so to give you a wide range of adjustability in the frequency of the notch. The balance control pot is up here. That will need to be cleaned. The wipers on that will need to be cleaned as well. Here is the rejection amplifier. It's the active part of the amplifier circuitry that's tied into the wean bridge circuit to provide the notch filter to notch out the fundamental frequency. Over here is the opto isolator module that has the incandescent light bulbs along with the photoresistors that control the automatic fine tuning of the wean bridge notch filter. I'd like to open that up and show you what's inside of that. Maybe we'll do that with my other 334A, so I can leave this one where it is, but I'll open up the other 334A and show you the insides of this module so you can see those photoresistors and those incandescent light bulbs. That should be interesting. Maybe we'll do that. The frequency range switch with all its associated resistors, and not much to see there, but the switch contacts are dirty on this as well. I will be cleaning those. This is the phase detector and the error circuit that measures the amount of error in the automatic fine tuning. And there's one screw over here that holds this board in place, and then when you remove that one screw, it hinges up so that you can access the board underneath. Underneath is the main meter amplifier circuit. This is the main voltmeter circuitry right here underneath. And of course, in the back is the power supply board. Most of these boards are interconnected with these crimp-on terminals that push onto these little pins. Now, the terminals themselves, the female socket crimped-on connectors are silver plated, and yet the pins that they push onto are gold plated. And somehow there's some incompatibility between the silver plating and the gold plating, and resulting in some corrosion of the silver plate, right? And that has caused some intermittently bad connections along all of these terminals. Look how dark some of these are. I will have to clean each and every single one of these terminals and each and every single one of these silver plated connectors and seat them onto their associated pins. I'm going to do that off camera. I'm not going to go through that with you because you've seen everybody clean contacts before. But I will do that with every single connection on this instrument, including the ones down here, and plus cleaning all the switch contacts on the rotary switches and all the wipers on the pots, because there's several little flaky intermittent problems actually with this instrument, and that's all caused by these poor mechanical connections and dirty switch contacts and so forth. So that's what's up on my list. But let me open up this photo module and show you what's inside of it. All right, so I've removed the photo module from the instrument. This is from actually out of my other 334A because I have two of them, right? So I didn't want to mess too much with the one that I'm currently working on, but this is a separate one from the other instrument that I removed. Okay, and all of those crimp-on connectors push onto these gold-plated pins. Of course, these have been cleaned already. On the back of it, one screw that removes the circuit board from the black plastic outer cover. Right, pull that out. Use a posi drive screwdriver for these screws, by the way. It's not a regular Phillips screw, it's a posi drive screw. And once you remove that one screw, the circuit board comes right out. There's a little bit of foam inside just for cushioning, right? And here we see what's inside the instrument. We have two incandescent light bulbs, and there are actually four of these photoresistors. There's those cadmium sulfide resistors with little windows on the front of them that the light shines into. It's going to be hard to view them. Maybe I can zoom in. I don't know how well you can see that, but on the front of this little photoresistor is a little window, and that shines onto the cadmium sulfide element in there. That is a resistor that when it's illuminated, it is quite low resistance, and when it's dark, it's extremely high resistance. And there are specifications for these, what those resistances should be. And in fact, there's an adjustment procedure that where you are supposed to put a specific voltage on the light bulb so it has a specific brightness, and then you move the photoresistor either closer to the light bulb or farther from the light bulb to adjust it for the proper resistance while measuring across it. um, that will ensure that you have the right amount of range in automatic tuning of the of the notch filter. This is for the balance control. This one single photo resistor by itself, and these four over here are for the reactive leg of the wean bridge. The two for the series part and two for the parallel part. Um, there, there's a wide range because it's in a feedback loop, so there's a wide range of adjustment. And if you have it slightly off, it'll still work okay. But if you have it severely misadjusted, like not pointing in the correct position near or far from the light bulb, then there won't be enough range on the feedback to correct for that and won't be able to properly tune the notch filter. These are adjusted at the factory, and I suggest you don't really mess with them, although it is possible to do so. There is a procedure that's completely fully outlined in the manual if you need to do that. Or if the light bulbs actually get burnt out or broken and you have to replace the light bulb, then certainly we'll have to readjust the position of all of these photo resistors. So that's what's inside the photo module, the A6 assembly in the 334A. All right, so after cleaning all the contacts, I reassembled everything and went through some of the adjustments, and now it meets spec on every range. So we have another completed 334A distortion analyzer. So that'll do it for this episode. Thank you very much for watching. Please like and subscribe, and stay tuned for more fun videos with vintage Hewlett-Packard test equipment and other fun stuff. Thanks again. What do you think, Hopper? Does it pass inspection? She doesn't seem all that interested.